Okay, so today I want to go a little bit quickly. We've already covered part of the map. Oh, before I forget, the exam one, test one is now available on Canvas and through grade school. So part one, like I mentioned to you, is like a few multiple choice questions, and then part two is long answer questions. You have approximately 48 hours. I think Sunday night is when I made it due. So that's when you have to turn the take home exam. If you have any questions, please email me. I realize it's on a weekend, but I also thought that's better because it's, I was trying to make it so that you don't have other exams during the week that you have to worry about. You can just focus hopefully on this over the weekend. It's not ideal. The weekend is kind of a little bit maybe ruined, but I figured it was better than trying to give it to you. Okay. If you have questions, email me. I'll try to get back to you, as soon as possible over the weekend. Okay. So for today's lecture, as I said, we covered electromagnetic waves in the last class, and we just started talking about linear polarization. So let me quickly remind you. So because light is a transverse electromagnetic wave, it has a vector nature between the vector components of E and B and the K, the direction of propagation, which as we saw is always a right-handed triad. And it also means that this vector nature, there's some information in this vector nature of light, which is very different than most other waves that we encounter in light. So this state that describes that information is called the polarization of light. Okay. And as we saw, we can have two components for E, which is the X component and the Y component, which are denoted by which can take this general form when the Z-axis is the direction of propagation. And you notice this extra little epsilon over here. That epsilon represents the phase between the Y and the X components. And for epsilon greater than 0, the Y component will lag behind the X component. That's because of this minus sign in this omega t. Yes.
Yeah. So the component is the right hand epsilon1, epsilon2, and then K is epsilon1 cross epsilon2.
Correct.
So
it's a right-handed triad.
Yeah. This is global and this is global. And then the just the local coordinates will describe everything. Will tells us everything, right? So this coordinate is the global coordinates, and
it propagates along with the beam.
Yeah.
Okay, so now let's consider some examples, cases of this, which will hopefully make it a little bit more clear what I'm talking about. Okay. So when epsilon first, the simple case we'll take, that phase difference between the X and the Y components is 0. Okay. And we're also, for simplicity, going to assume that the X component and the Y component of the electric field are equal to each other. So E naught X and E naught Y are equal to the same value, which is E naught. Then the electromagnetic field, the electric field vector can be written in this form, right? I just took that previous equation and I put E naught X and E naught Y equal to E naught, and then put the epsilon equal to 0. So I can take out the cosine K Z minus omega t common to both the X and the Y component. It's outside the vector relationship. Okay, so then the state of this electromagnetic wave can be described as a 45-degree polarization. That is, it's in the first and the third quadrants. The electric field, as the time evolves, will always remain along this first and third quadrant in a line, which is at 45 degrees with respect to the X and Y component. Why is that? Well, we can see that by considering what happens at, say, time t equal to 0. Okay. So, and also by fixing Z. So Z could be fixed to anything. Okay. Let's say initially we fix Z to be Z as well. Okay. So then this is cosine minus omega t. And for cosine minus omega t is the same as cosine omega t. So that's just cosine omega t at Z equal to 0. Then, and always we draw this sort of this X and Y axis looking backward into the beam. Okay, so imagine that we are an observer sitting right over here, looking backward toward the source, which is producing the electromagnetic waves. So we're looking backward along the beam, and we are drawing the X and the Y axis and the X and Y components of the electromagnetic field, because that's really what affects us, which is what is the X and Y components at the location of the observer. That's what matters. So that's why we take this convention that we're always looking backward into the direction of propagation, into the laser, etc. Of course, don't use your eye from the laser, but this is the idea mentally. So at time t equal to 0, let us say that the x and y components are now both, because cosine of 0 is just 1. So now we have x e naught plus y e naught, which means that that's exactly exactly 45 degrees. So it's a e naught and e naught, which is exactly equal to each other. Okay. Now, maybe it'll be easier if I just do this on the board rather than trying to go through it on this slide. So I said I'm looking at its x and y components. The electric field vector is equal to x hat e naught plus y hat e naught times cosine kz minus omega t. And always, whenever you get confused about what the state of the electromagnetic field is, the vector, I encourage you always to go back to that original definition. What E naught x is, what E naught y is, put in the phase difference and work it out, and you'll never go wrong. Okay, because it can be difficult sometimes to remember which phase is what and how do I figure it out. Well, as I say, if you go back to the original definition, then you'll never go wrong. So let's say that at time, so let's say kz equal to 0. So I'm at z equal to 0, and let's say I'm at t equal to 0. So then E at this value is simply x hat E naught plus y hat E naught. Okay. All right. So that means I'm at component E naught along the x-axis, component E naught along the y-axis. I remain at 45 degrees angle with respect to the x-axis. So at some time t later, okay, so again, because cosine of minus omega t is equal to cosine omega t, doesn't matter. So at some time t, let's say positive, some value, say 10 degrees, cosine omega t, as you know, if I just plot cosine omega t over here, is going to go down, right? And when omega t equals pi over 2, that's when it goes to 0, and then it goes down to -1 at omega t equal to pi, and so on and so forth. Okay. So I'd say some little value, I don't mean t equal to 10 degrees, omega t equal to 10 degrees, let's say. Okay. Then you can see the cosine value decreases. Okay, so now if I were to plot, again, I'm now doing this at a second time. Now if I were to plot this, it's no longer quite at this value, this maximum E naught, it's some smaller value, right? Something else, E naught prime, call it, whatever that is, which I can just find from putting in now E equals x hat E naught plus y hat E naught times cosine 10 degrees, right? So that's what I would do. So now each of these components is E naught cosine 10 degrees, E naught cosine 10 degrees. So in fact, I can write that cosine 10 degrees. This is E naught cosine 10 degrees. So as we can see, because cosine 10 is slightly lesser than 1, so therefore this will be slightly smaller in value, but you can see the relative relationship between the x and the y components remains the same. They're exactly equal to each other. So this is still 45 degrees. Okay. Continuing in this way, you can see as I go down to say cosine omega t equal to pi over 2, now both of these go to 0. So now my vector is now right at the origin. Okay. I can't really define a state of polarization at that point, but it doesn't matter because that is just an instant of time. You can see again for like slightly greater than pi over 2, now they will both flip sign, both will become negative, x and y will become negative, right? Because that's what happens here. Cosine omega t becomes negative, and that's multiplying both the x and the y component. And therefore, now basically you can see for yourself that it will go all the way to this other side. And at what time will it go to exactly minus E naught and minus E naught on both sides? When does that happen? When will both x and y component reach minus E naught and minus E naught? Yes? Fine, exactly. So we see that, and then again, it's going to retrace back, and finally at 2 pi, it will come back again to the original point. And therefore, we see that the line of polarization, as it is called, or the plane, we call it the plane of polarization, is basically along this 45-degree angle with respect to the x and y coordinates. Any questions on this? 45-degree polarization. Now, of course, if E naught x and E naught y were not equal to begin with, right, you can say this angle will change, right? So if E naught x is not equal to E naught y, okay, then we have to write this E as x hat E naught x plus y hat E naught y. But let's say the phase is again 0, so it's cosine kz minus omega t. You can see all of the same arguments that I just used will go through, except that the angle that I originally start with will be different, right? So the original angle will no longer be 45 degrees. It will be some value which is given by some angle theta, right? Which is going to be tan inverse of E naught y by E naught x. Does everybody see that? So if I write down this E naught x as some angle E naught cosine theta and E naught y as E naught sine theta, this is now theta is the angle of polarization. People sometimes write it as theta or alpha, whatever you want to use, maybe alpha if you prefer. But this angle of polarization will then be given by E naught y divided by E naught x and then tan inverse. Okay, so nothing has changed, just I'm at a different angle here, and then I still live sort of in this quadrant, first and third quadrant, because the cosine kz minus omega t is common to both the x and the y component. So it just continues along this line, but the line is now tilted with respect to the 45. It's no longer 45 degrees. Okay, so now I'll take a slightly different case, which is some reason if I'm showing the screen. Now E naught x and E naught y are equal again, equal to, oh, sorry, that's just the case I just covered. That's also, okay, now, oh, oops. Okay, I went too fast, but it's okay. Now you can imagine epsilon is not just 0, but it's pi. Okay, so the phase difference, you remember I said if epsilon is greater than 0, it means the y component lags behind the x component. Okay, so now the y component is lagging behind the x component, and E naught x and E naught y are equal to E naught. Okay, and again, if you carry out the math, sorry, I should probably done this first. Okay. I can't read it there. Okay, so I'm going to have it. Maybe you're all aware of this math, but in case you're not, then I'll just show it to you one time, which is which is that if I have some function cosine, okay, of A minus B, then this is cosine A, cosine B plus sine A, sine B. Or if I have a plus sign here, then this becomes a minus sign over here. So we can do plus minus here is equal to minus plus in this difference between those two cosine in this terms. Okay. So what we had in that earlier expression is cosine kz minus omega t plus epsilon. Okay. So if I treat this as A and this as B, okay, so we get that this is cosine. I'm just writing it as A, you know, it's kz minus omega t, cosine B, which is now epsilon, plus, minus sine A, sine epsilon. Okay. So now if epsilon equal to 0, we already saw sine epsilon goes to 0, so that term doesn't matter. We just get this, which is what we got earlier. Cosine 0 is just 1. So we got cosine kz minus omega t, which makes sense. But if epsilon equals to pi, right, then this is cosine A, and then cosine of pi is minus 1, so I get minus cosine A, right? And I get for sine epsilon of pi, what is that? Does anybody know? 0, exactly. So we get that this is minus cosine kz minus omega t. Okay. So this gives us minus cosine kz minus omega t. Okay. And I also, since I'm here, I may as well also do the other case, which is epsilon equal to minus pi over 2, or plus pi over 2 is also obviously possible. So now when cosine is equal to minus pi over 2, this becomes cosine of A, okay, but cos pi over 2 is 0, right? So we get 0 minus sine A times sine pi over 2, which is just 1. Okay. So we see all these different possibilities, but what this is saying now is coming back to here, right? Well, I guess I didn't write it here, but so E, remember, was x hat E naught x cosine kz minus omega t, if y hat E naught y cosine kz minus omega t, and I've just shown you for epsilon equal to pi, that now comes in with a minus sign, that second term, the part that is multiplying the y, the E naught y, that must now come in with a minus sign. So my new function for this polarization, if I were to write this for epsilon equal to pi, for epsilon equal to pi, this E naught, this electric field vector must now be written as x hat E naught minus y hat E naught times cosine kz minus omega t. Okay. So, and similarly for epsilon equal to minus pi over 2, this becomes minus sine A, which is sine kz minus omega t. And I may as well write that one as well. So, we'll cover that in just a second. So for epsilon equal to pi over 2, minus pi over 2, this E hat or E, the electric field vector is x hat E naught cosine kz minus omega t. That part remains the same because there's no epsilon there. But then the second now has minus y hat E naught sine kz minus omega. So this is for epsilon equal to pi. This is for epsilon equal to minus pi over 2. Okay. Where of course Ey then leads the Ex component, and we'll cover that in just a second. Okay, is this math clear to everyone? So math part. Any questions on the math? So hopefully now, for the epsilon equal to pi case, you'll understand why we got this equation. I just wrote the derivation over there. And as soon as we see this, we know now that remember the cosine being outside means that the relative angle between this x and y component is just going to remain the same, no matter what time you're at. Because as cosine omega kz minus omega t changes, it just still keeps everything along the same line, but just the actual value of the field along those two components changes, but it remains in lockstep with each other. The x and the y components are basically in lockstep with each other. And all that's changing now is this relative angle. So you can see here, now the relative angle is going to be minus 45 degrees. Okay. So the line, instead of being along the 45-degree axis, will be along the minus 45 or 135-degree axis, whichever way you want to view it. And that's what is shown here. So this field will remain in this minus 45 direction. And you can see it just stays, starting from here, going down here, and then coming back that way. Okay. And now the line of polarization then is, as I said, it's in the second and the fourth quadrant. Okay. So that's the difference between epsilon equal to 0, epsilon equal to pi. And now let's cover the, yeah, okay. So now what about how do we create such states of light? One way in which we can create such a state of light is by using something called a dichroic polarizer. Oh, oops. So what happens in a dichroic polarizer is that it selectively absorbs one of the polarization components, either X or Y. Okay. So when it does that, if you start out with light which has an equal mixture of the X and Y polarizations, and I can just absorb one of the components, now what you end up with is a component that's entirely along one axis or the other. Okay. So here in the microwave frequency, it's actually quite easy to do this by hand. Okay. So like at a few gigahertz, the wavelength of light is like 10 centimeters. So if you construct wires which are like spaced very closely apart compared to that 10 centimeter of light, then you can basically make all the electrons in the wires cancel out the component along that direction. So that is shown sort of pictorially here. If I have incoming light that's unpolarized, okay, so you can think of unpolarized light as an equal mixture of both vertical and horizontally polarized light, or X and Y polarized light. And what happens is if I take a wire grid with the wires oriented vertically, what comes out is the horizontal component. Now, this is always confusing to sometimes to people. They think, the space between the wires allows the vertical component to pass, but blocks the horizontal component. So I should be getting vertical polarized light, but that's not what happens. Instead, you should think about the electrons in the wires moving to the vertical polarization, okay, but not to the horizontal. The horizontal is unable to drive them because they can move freely along the y-axis, but not along the x-axis. The wires are like very thin compared to the wavelength, so it can't really move in that direction. Then those electrons, I mean, this is very non-rigorous, intuitive way of thinking about it, but that's what I think is close to the actual thing that's going on. Which is now those electrons that are moving along the y-axis set up a radiated or scattered field which cancels the light in that direction. Whereas the ones that are moving, this way would cancel that direction. Anyway, so the point is what comes out here is entirely horizontally polarized. This can be done at microwave frequencies by hand. Basically, people can just string wires together like this and they get polarizers like that. Okay. In the optical domain, of course, things are a little harder because now the wires have to be tiny space compared to an optical wavelength, which is usually hard to do by hand. But there are many crystals in which this occurs naturally. Okay, like tourmaline is like one famous example. There are a few others as well, where the wires, so to speak, are like molecules that have been stretched along one axis. And basically that allows you to set up the same sort of geometry. Nowadays, with our control over materials, we make plastics, basically polymers, and the typical like polarizing sunglasses that you get are basically working in this principle. They basically are pieces of polymer with like molecules that have all been oriented in one direction, and that orientation will screen out the polarization, which is along that direction, and allow only the parallel, the one perpendicular to that to pass. Okay. Also, if I now take two of these wire grid polarizers and start orienting them with respect to each other, that gives rise to something that we call Malice's law, which is now very hopefully simple for you to understand. If I now come out of one of these polarizers, and usually what we do is we define a polarization axis or transmission axis for this polarizer, so we can replace this entire picture by just some block, a building block, a polarizer, which has a transmission axis along the horizontal direction. Okay, so that's what we call the polarizer. It has a transmission axis along a certain direction. However you construct, whichever way you construct it, whether it's plastic, tourmaline, etc., the dichroic polarizer, whichever way you make it. There's also going to be birefringent crystals that I'll tell you about in a little while. So all of those effectively, you can think of them as having some transmission axis. And only the light that's polarized along that axis will get transmitted. The light that's perpendicular to that axis will get absorbed, or will not make it through to the beam that's going straight to. Okay. So now if I have two of these polarizers, okay, and you can understand now, coming out of this polarizer, the beam, the electric field is along this direction. If I now take the other polarizer and start rotating it with respect to that direction, only the component along the transmission axis, which is given by the cosine of the angle between the transmission axis of the second polarizer and this polarization, the horizontal polarization, only that component that's along that axis will get transmitted. And that's given by the cosine of the angle. So that's shown here. So here's the first polarizer with the transmission axis along this direction. Now the transmission axis has been oriented vertically. So the outgoing polarization is exactly vertical, okay, over here. Now the second polarizer has a transmission axis along this dashed line, which is at an angle theta with respect to the vertical. So the component of light that is transmitted, okay, will be E naught cosine theta, and the state of the polarization will now be at an angle theta with respect to the vertical as well. So the state of polarization after the second polarizer is along that transmission axis. That always is true. Okay. All that changes is how much of that electric field gets transmitted. Okay. So the amount of electric field that's transmitted is E naught cosine theta, right? Just by the vector relationship. And the state is along that angle theta. So if I ask you what's the state of polarization after this polarizer, it's at the angle theta with respect to the vertical. Okay. And the amount of the electric field is E naught cosine theta. So the intensity is going to be square of that, as we have talked about before. And I'll derive that in more rigorously in a minute or so. That is going to be E naught squared cosine squared theta. But E naught squared was the original intensity, because that's proportional to the electric field along this direction. So this is I naught cosine squared theta, which is called Malice's law, which you have verified now in your lab experiments. Any questions on that? Why it's I naught cosine squared theta? This is very important. This general idea, principle is very important. So even if you don't remember the law, you should be able to reason based on just this fact that the transmission axis is at some angle, then the incoming electric field, only the component along that transmission axis gets transmitted. And the state of the polarization will remain along that polarization axis afterward. Okay. Okay. Okay, now we come to circular polarized light. So remember, I just derived this for you on the board. When epsilon equals minus pi over 2. Also, of course, I should note adding 2 pi or multiples of 2 pi to that doesn't change anything, because those trigonometric relationships are identical. So now we get a slightly different looking function for the electric field. E equals x hat E naught cosine kz minus omega t plus y hat E naught sine kz minus omega t. Okay. So this is the relationship now. And again, I've chosen E naught x and E naught y to be equal to each other, which is equal to E naught. Okay, so there are many ways to understand what the direction of polarization is, but I always like to go back to that initial diagram that I drew, and that's also, I mean, it's shown here in your textbook as well. So I put that drawing here. But since I can't always remember what it looks like, I just like to go back to the original expression. And please follow along with this because it's a confusing issue. So let's try to make sure that you get it. Okay, so we've written this over here, so I'll start here. So we have x hat E naught cosine kz minus omega t minus y hat sine kz minus omega t. Okay. Okay, I see. I made a mistake. When I was drawing this here, when I was writing this out here, cosine A cos epsilon minus sine A sine epsilon, which means when I put sine epsilon where epsilon is minus pi over 2, that gives me another minus. So this ended up being plus sine kz minus. Sorry about that. So this is still a plus sign over here. Sine cosine kz minus omega t plus y hat E naught sine kz minus omega t. So the best way again to argue is thinking about what happens when kz equal to 0. Remember that the observer is looking backward into the beam, but so we can cite the observer at z equal to 0 if we like. So that is just 0. So this E is equal to E naught x hat E naught cosine omega t. And now for sine, you have to switch the phase. So it becomes minus E naught sine omega t. The sine of minus omega t is minus sine omega t. Sine is an odd function. Okay, having said all that, now let's look at say omega t equal to 0. Then cosine omega t will be 1, sine omega t will be 0. Okay. So our electric field vector will be entirely along this x-axis. At some time omega t a little bit later, let's say omega t equals pi over 4. Okay. Then at E at omega t equal to pi over 4 will be x hat E naught. Then cosine of pi over 4 is 1 over root 2 minus y hat E naught. Sine of pi over 4 is 1 over root 2 as well. So we see that at omega t equals pi over 4, the electric field vector must be pointing downward like this. Okay. Because that's a minus sign in front of the y component. And the total, of course, the magnitude can't change. So this is still E naught. This total length of this vector is still E naught. Okay. Again, going on one more step, omega t equals pi over 2. We know that cosine of pi over 2 is 0, sine of pi over 2 is 1, and this is therefore minus y hat E naught, so it's just E naught. So you can immediately see that basically this is going to be a circle, okay, with the direction of the electric field vector circulating clockwise. Looking backward into the beam, this is clockwise rotation of the electric field. This is called right circular polarization. Okay, and hopefully it's clear then if I switch that epsilon to be plus pi over 2, it would circulate the other way. So we would get left circular polarization. We only have 3 degrees of freedom really to play with in the polarization. One is the ratio of the amplitudes, that is this E naught x and E naught y, right? Whatever that is, because the magnitude remains fixed in most polarizers, they're not very lossy things, most situations, we try to reduce the loss. So polarizers, wave plates, whatever it is, we don't want any loss in the wave plate. So E naught X and E naught Y, the sum always hopefully remains close to the original E naught, the magnitude. All we can play with is the relative ratios. So for example, with the polarizer, as I orient the angle of the polarization, I can change the ratio between E naught X and E naught Y through that cosine of that angle. And I can play with this phase. The phase here was pi over 2. It could be anything, of course, and we'll cover the most general case in a minute. So those are our three variables essentially that we can alter. Okay. Okay, if there are no questions about this, I will move on. Okay, so that's summarized over here. I'm just going to quickly go through this. So that's exactly what I just said. I just started the drawing from a different point in time. Basically, I started with it along the y-axis and talked about what happens as you go further. Okay, so that finishes that, and then we have the left circular polarized light, which is for epsilon equal to plus pi over 2. All right. So for epsilon equal to plus pi over 2, we get this term over here, and you can argue for yourself why that's left circle. Okay. So we have talked about right and left circular polarization, but the more general state, of course, like we've just said, I'll hide that, so I'm not going to try. The most general state of light is when E naught X is not equal to E naught Y. And let's say first we start with the simple case where epsilon remains pi over 2 or minus pi over 2. As you know, that just changes the direction of the circulation. It'll be either left or right, depending on minus pi over 2 will be right, plus pi over 2 will be left. So now if E naught X and E naught Y are not equal, you can see instead of going in a circle, it's going to go in an ellipse. So if E naught Y is greater than E naught X, then it'll start initially with that E naught Y, and then it'll circulate like that. Right circular for epsilon equal to minus pi over 2, or left in this case for epsilon equal to pi over 2. And then the opposite situation. E naught Y is lesser than E naught X. Now this ellipse looks more, the major axis is along the X direction. Okay. So that's one general state of polarization beyond the circular polarization. It looks very much like circular, except that the amplitudes E naught Y and E naught X are not equal to each other. I'm not deriving rigorously what happens in these cases. If you're interested, you can look in your book, but usually we won't worry about having to derive those situations in this class. Okay. And then the even more general case is when E naught X is not equal to E naught Y and epsilon is not equal to some function of pi, meaning some multiple of pi or some odd multiple of pi over 2. Okay. So like, pi over 2 is an odd multiple 1 times pi over 2, and it's also not any integer multiple of pi. Okay. So for example, I could choose 45 degrees, just as an example for epsilon, or pi over 3, for example. Some general value of epsilon, any value other than those values. Then this ellipse that we were talking about, right, is no longer oriented along the X or the Y axis. It's oriented along some other direction, some other major axis and minor axis, which is shown by these dashed lines over here. and that dashed line has some angle alpha. And actually, this is typically the state of polarization. If you take, for example, 45-degree polarized light and you put it on something like a piece of glass, a lot of times what comes out is going to have, which, it depends on the glass or the mirror, etc. But a lot of times what's going to come out is the elliptically polarized light, okay? Which you have probably all kind of seen in your class, in your polarization by reflection experiment. I'll talk about that in a minute. Now, of course, that is if that means that you must introduce some phase shift beyond these phase shifts, pi over 2 or pi. The experiments that you did, you were not able to introduce that in a controllable way. Usually you couldn't do that, so therefore you still end up with linear polarized light coming out. But if you can now create some phase shift between those two waves, such that it's not a pi over 2 or pi, etc., then you start to get, elliptically polarized light and so on. So I'll talk about that in a minute. But this is just the most general state. Again, you won't need to know the derivations. I just want to give you have that intuitive picture of why you might get such a polarization state. So finally, I'll talk about unpolarized light here. So you can think of this as linearly polarized light, but the angle of polarization is not fixed, but it changes randomly very, very quickly, so quickly that we can't follow it. Okay. So when you think of it that way, it's like saying that there's analogies here to quantum mechanics, but I won't get into that. Between pure state of a quantum object and a mixed state or density matrix
in that case,
that describes a quantum object.
We have to do the second quantization to the electric field and magnetic field, and then calculate the expectation value, and then we have to calculate here we have to, for fluctuations, we determine the correlation functions of the correlation functions like on two sides.
You could, but a more simple picture is to think of the state of the photon as being described by a density matrix rather than a pure quantum state. Yeah. Okay. So again, as I just said, if I think of the polarization state as fluctuating randomly, remember Ex0 is E naught cosine alpha, Ey0 is E naught sine alpha. And now both cosine and sine, if that alpha is a random variable rather than being a fixed value, okay, that's how you should think of this polarization state. So this alpha is no longer fixed, but it's a random value that fluctuates very quickly. So that in any one observation of the polarization, we are averaging over all the possible directions of the polarization. Then in that case, you can show that the average value, of course, of the Ex0 and Ey0 is 0. So it doesn't have any particular direction of polarization, but there is the variance, so to speak, just like any random number, the mean value will be always 0, assuming you've subtracted away some constant mean value, but the variance or the fluctuations doesn't vanish. And you can show that fluctuation is E naught squared over 2. And remember, the intensity is dependent on the square of these components, Ex squared and Ey squared. So you get half of the intensity of the initial unpolarized light. Okay. So we can think of it as two independent light sources of orthogonal polarization, but we no longer can write down a simple expression for electric field. Instead, we have to go to this higher order description. But again, just to keep that in mind, we'll talk about it when we do the polarization, when we put a polarizer in front of it now. So if I think of it as two independent light sources, one oscillating along X, one oscillating along Y, and I now put a polarizer with its transmission axis only along that light bulb's direction, then what gets transmitted is only that light bulb or that polarization, but with half the intensity of the original, because the other direction has been cancelled out. Okay. So that's why when I take unpolarized light and send it through a polarizer, I'll get the correct polarization. Of course, we know that's what a polarizer does. You can think of it as filtering out all other states except the one along the transmission axis. But the intensity has reduced by a factor of 2, which means that the magnitude of the electric field is reduced by 1 over root 2 compared to the original magnetic electric field. Anyway, okay, that's just about unpolarized light. So in the last few minutes, we've covered one description of how to do polarization by using a wire grid polarizer or dichroic polarizer, as we call it. That's the most general term for a polarizer that operates by absorbing one component with respect to another component. But we can also use another technique, which you've all seen in your lab, which is polarization by reflection. Okay. So in polarization by reflection, we take this situation. Here is your interface of the glass material, whatever it is that you have, and we now take two situations. In the first situation, remember that K, E, and B always have to form a right-handed triad. Okay. So initially, if I take E to be pointing out of the screen, which is denoted by this circle with a black dot on it, one way to picturize that is imagine there's an arrow and the tip of the arrow is facing towards you. So then what you would see, what I would see is just that little dot and then the head of the arrow. That's the E field, and then the B field must be lying in the plane of this board or the screen. Okay, because E and B form a right-handed triad, and the direction of the electromagnetic field is going this way. Similarly, when it bounces off of this interface and goes in that direction, again, E and B form a right-handed triad, and this electric field vector still remains along perpendicular to the screen, pointing out of the screen. And as you can see, the transmitted wave, the same thing happens. It's still E and B are again in that right-handed triad form. Okay, this type of polarization where the electric field is pointing out of the screen or out of the plane of incidence. Okay, this is the plane of incidence right here. That is called S polarized, or sometimes called TE polarized, or also referred to as vertical polarized or perpendicular polarized. Okay, all these different names are often given for it. In this situation, RS, which is the coefficient which gives you the ratio between the reflected S state of polarization and the incident S state of polarization, R sub S, that is greater than 0, as you can see, because the electric field is still pointing out of the screen. If it were to go lesser than 0, then it would point into the board, okay? And that would be given by, a symbol with like an X in it, okay? This you may be familiar from when you talked about magnetic field lines or something like that. We always denote those field lines going into the board with the X, and the field lines coming out of the board as having the dot, okay? So same idea here. So here, the electric field is always pointing out of the board, and the situation I have sketched implies RS greater than 0, the reflection coefficient greater than 0, because the S component of the electric field has stayed in the same orientations. We can also look at the P component of the or P polarization, or what we call TM polarization or horizontal polarization. Now the electric field vector lies in the plane of the board or the screen, and the magnetic field now has to point out of the board, right? Again, if you do a right-handed triad from E to B, that has to lie along the K-axis. That's why the B direction has to be pointing out of the screen. Okay. Same thing here. E and B have to lie in the right direction. So again, that is the orientation of E and B. Now it doesn't have to be. If E is flipped, if it goes over to this direction, then B would have to go into the board again to maintain that orientation. And the idea, of course, is again I have shown RP greater than 0. This particular orientation is such that RP greater than 0, that's because we have that when the electric field, its component along the normal is always pointing upward, it's positive. That is, if this is the normal, if I chose this as an axis, then the component of E along this axis remains positive in this orientation. So RP, the reflection coefficient, is also now in this convention greater than 0. That its polarization or its direction is the same, meaning it's always oriented with the component along the normal as positive, upward, pointing upward along the normal. So this is the sign convention for the polarization, and that's also known as TM polarization or horizontal polarization. So now I'm not going through the math of this. I'll post a separate video. We can derive the Fresnel coefficient from Maxwell's equations. Okay, and when we do that, we get this graph. First I'll just show you what's in the graph before I show you. So we're plotting RP and RS, those two reflection coefficients. And this is the Y scale, and the X scale is just the incident angle of that beam on the block of glass or dielectric. And what we find when we plot the reflection coefficients for these two conditions, RP and RS, we find that RS is always negative. Remember that electric field vector that I was showing you as RS greater than 0 means the electric field vector stays in the same direction, out of the plane of the board. Okay, it's perpendicular to the plane of incident. What this is saying is RS is always negative for theta lesser than 90 degrees, which is the only directions we need to worry about, 0 to 90. Okay, So in that condition, RS is always less than 0, and RP stays initially positive, just like we sketched on that previous slide. But then at one point, it goes to 0. Okay? And then it starts going negative, so that it's now going down here. And then we finally come down to this angle where you can see you get perfect reflection, right? -1, basically, for both the coefficients. What is that? First, this angle where RP goes to 0, which means there's only RS. So even if I started with unpolarized light, which can be thought of as a horizontal, half horizontal and half vertical mixture of light, at this particular polarization, the TEM polarization goes to 0. The reflection goes to 0. And I'm only left with the perpendicular component, that is the vertical polarization coming out from the block of glass. So only that part will be reflected from the block of glass. Okay. And then at 90 degrees, which is, again, I'm sketching the different angles over here. So at some angle, say theta, which is the Brewster angle, you'll get a reflection with just the vertical polarization. And at some angle close to 90, which is when the beam is almost parallel to the surface of the glass, almost, then you get perfect reflection of both the vertical and the horizontal components. Okay, they're both perfectly reflected, which makes sense. We know that when we look at things, that are like this, you get nearly a perfect mirror type finish when you look along that direction of the glass. Okay. I was going to show you the rotation angle for this picture, but I don't have time today, so I'll talk about that in the next class.